Digital Logic Project, presented by Michael Siahaan and team members Faisal Abdul Hakim, Anwar Abdul Rahman, and Anwar Hidayat. The issue at hand, our objective was to create a well-crafted circuit that could serve as the fundamental framework for an elevator system. We carefully examined and worked on the requirements provided to us to ensure that our circuit met all the necessary criteria. In the next slide, we'll provide a detailed list and explanation of the tools that we utilized to accomplish this task. Criteria and other notes. In accordance with the curriculum requirements, we'll utilize the specified tools while constructing the project. However, we aim to enhance the system's functionality and practicality by incorporating additional circuit elements. These additional components will be carefully selected to ensure that they complement the existing tools and contribute towards the overall performance of the system. Basic Circuit 1, 3-bit synchronous counter, JK flip-flop, up as 0, down as 1, and comparator using XNOR gate. Basic Circuit 2 used its components. So the example for our project, a hostel visitor wants to use a building lift to go up from one level to another. The requirements are to put in the desired level to go, tag the visitor room card, close the lift door, and push up button. Then the lift will go up by counting up one level to another until it reaches to the desired level. The door will open and at the same time, alert will be given to the visitors. Similarly, the reverse process happens when the visitors want to go down. The counting sequence will decrease until it reaches to the desired floor. So for lift up, you need to key in level up, tag in card hotel, the door closed, lift goes up to destination, lift stops at destination, sound notification, and then the door will open. For lift going down, key in level down, tag in card hotel, door closes, lift goes to the destination, lift stops at the destination, sound notification, and door open. The timeline for our project is as below. On the 16th of January, our team chose the aforementioned project type and founded our group. On the 20th of January, we began our discussion of what type of application we could base our circuit on. On the 26th of January, the team decided to choose a circuit based for an elevator system and tasks were distributed among members. On the 3rd of February, our circuit was finished and we began working on the presentation report and video accordingly. On the 7th of February, we were finally done with all of our tasks and font checks were made. The outline for our project, the circuit will use the previously mentioned tools for moving from floor 0 to floor 7. It will have the ability to identify its current position and desired destination, accept multiple inputs, and use a combination of all inputs to achieve the desired outcome. A comprehensive explanation of the various sections of the circuit will be provided on the next slides. For section A, the elevator system we have in place relies on 3-bit synchronous counter that comprises several logic gates, including AND, OR, and JK flip-flops. This counter plays a crucial role in ensuring that the elevator operates flawlessly and efficiently, counting the number of floors the elevator passes through and keeping track on its position. Overall, this intricate counter system is what enables our elevator to function smoothly and safely. This is the state diagram showing the transition of 3-bit synchronous counter used to portray the function in slide 7. And from the above state diagram, you can make this state transition table by taking mode Q2, Q1, and Q0. For the K-map, we can use them to find J0, K0, J1, K1, J2, and K2 by entering the values we found for each of them in a K-map. This K-map is made based on the above state transition table, from which we can find the inputs of J0, K0, J1, K1, J2, and K2. The input called mode is the output from the comparator discussed in slide 12. The comparator checks if the section A is greater than section B. If not, it outputs 0, which will make counter count up. If A is indeed greater than B, it will output 1, making the counter count down. Section B. The section allows you to select the desired floor. If the selected floor matches the counter output, the system will send a 0 signal to the AND gate, which will stop the clock from transmitting a signal. The AND gate also considers the input from the switches, which indicates whether a card has been swiped and whether a power outage has occurred. Both of those have to be 1 for the clock to be able to send the signal. This section is a crucial component that compares two input signals A and B and generates an output signal indicating whether A is greater than B. It essentially functions as an automated switch controlling the mode of the counter up or down based on the comparison result. For titular explanation, the LIP operating system requires three flip-flops to manage 3-bit inputs that corresponds to floor 0 or ground floor to 7. We also use a comparator that utilizes XNOR gates to compare the string inputs, the button inside the lift, with the current floor. The comparator output is then connected to an AND gate, which serves as a clock for all of our flip-flops. This AND gate has four inputs, including card entered, clock, electricity outage, and the output of the comparator. To operate the lift, all three inputs, card, comparator, output, and electricity must be 1. When the output of the comparator becomes 0, or indicating that the input floor and the current floor are the same, it disables the clock for all flip-flops, causing the lift to stop at the input floor. That's it for our presentation. Now we're going to move on to our demonstration. So this is the circuit that we've made. As you can see, the one on top is section A that is going to indicate the current position of our lift, this one, and also the counter for our circuit. And then the one in the middle is our section B. This part is going to be our input or the buttons inside the lift. And this is our comparator that is going to compare the inputs or the button pressed inside the lift and the outputs of all of our flip-flops. And when the output of the section A and section B is the same, the XNOR gate will output 1 and the AND gate will output 0, so that this AND gate that serves as our clock enabler will output 0, essentially causing our circuit to not operate or indicating that the lift current floor and the inputted floor are the same. In contrast, if the output of our comparator is 0, our XNOR gate is 0, the comparable NAND gate will output 1, indicating that the current floor of the lift and the floor inputted is not the same, thus continuing the process of our lift. If the lift is going up, it will continue to go up. If the lift is going down, it will continue to go down. And the one on the bottom is section C, which is going to compare uh, if section A is greater than section B or section B is greater than section A. If section A, which is the current floor of the lift, is greater than section B, the floor that we are inputted or the button pressed inside the lift, then this comparator will output 1, indicating uh, that's going to ask the lift to go down. So, for example, if the current floor is the fifth floor and the button pressed is the first floor, so fifth floor is greater than first floor, so the comparator will output 1, telling the lift to go down. Uh, let's just jump right into our demonstration. So for the sake of demonstration, we're going to set free bar and clear bar to 1 to put it to synchronous mode. And let's just say the visitor have their card swiped and the lift has access to electricity. So as you can see, the lift is currently at the ground floor, and let's just say we want to go to the fifth floor. Okay, so the section B or the inputted floor is greater than section A or the current floor that the lift's at right now. So the comparator in section C will output 0, essentially telling the lift to go up. Okay, let's try it out by pushing the clock button. So the current floor is at 0 and we're going to the fifth floor. We push the button now. Okay, first floor, push again. Second floor, push again. Third floor, push again. Fourth floor, and again, fifth floor. Okay, if we push the clock button any further, okay, as you can see, the lift will not go up no anymore because the comparator in section B is outputting 0 or the current floor and the input floor is the same, thus disabling the clock per hour flip-flops, stopping the process of the lift. Okay. Now let's say we want to go down. Go down by 1 floor to the fourth floor. Okay. Let's see what happened. We push the button. Okay, the lift goes down and we push again. The lift stays at the fourth floor. That is because the comparator is outputting 0 because the current floor of the lift and the input floor is the same. And also the lift goes down because the comparator in section C dictates that the section A, that is the fifth floor before this, is greater than section B, which we inputted fourth floor. So 5 is greater than 4. So the comparator outputs 1, telling the lift to go down. Okay. Now let's get more example. Um, we're from the fourth floor and we're going to go to the seventh floor. Okay. So this section C will be inputted with this input from the seventh floor, section B, and from the section A, the outputs of the flip-flops. Okay. So because section B is larger than section A, the flip-flop, the comparator will output 0, telling the lift to go up. Let's take this example. Let us push the button. Okay, fifth floor, push again. Sixth floor, push again. Seventh floor, and if we push again, the lift stays at 7. Okay, for the last example, maybe let's go to the ground floor. Seventh floor to ground floor. Okay, because section A is greater than section B, the button pressed inside the elevator. So the comparator in section C will output 1, indicating the lift to go down. Let's push the button. Seventh floor, push. Sixth floor, we push again. Fifth floor, we push again. Fourth floor, we push again. Third, third floor, push again. Second floor, and last time. One, first floor, one more time. Okay, the ground floor. Any, and if we push any further, okay, the lift stays at the ground floor and it will not go anywhere. Okay, so basically that's for our digital logic project. Thank you for watching. Thank you for listening. Um, Happy vacation. Bye.